and of the FDP as well. Yes, so let us start it. Basically, in our FDP, we have covered the syllabus was presented. Let me open the canvas for you. So those who has not joined till now, I'm just showing this is the canvas. You are going to join. I have shared one link. You have to join through that. And every lecture I have put over here, there is file. I hope you can see on the screen. There is file. In this file, if you will click on this file, you will find all the PPTs available over here under the lecture material. So click on this lecture material. It is the lecture material. My cursor is moving. This is the lecture material. Click on this. And I have uploaded all the things related to all the lectures or whatever I have received from all the speakers. I have uploaded over here. So please access all these files. You can download at your Canvas account. We have shared 2 quizzes. This is quiz number 1, which is still open. If it is not open and somebody is requesting, we will open it. And the second number quiz, most of you have attempted, and this will be open till 12:30 today. 12:30 means afternoon, till afternoon, till noon it is open. Yes. So what was the syllabus? This was the syllabus for this FDP. What we did in this, so I hope my screen is visible to all of you. The syllabus is starting from module number 1 to module number 4. This is the syllabus. I have taken from an AICT course, Electronic Materials and Circuits. That was the syllabus, AICT syllabus, and this particular subject is there in the minor given to minor in VLSI design and technology offered by AICT for electronics and communication engineers. What is the minor degree? Let us discuss the minor degree and the honors degree nowadays. So in earlier days, honors degree was like there was a percentage system, right? So in that percentage system, in some of the universities, if you have more than 70%, then I'm audible. Please type in the chat box so that I can understand that yes, I'm audible. Audible? You want me to open the quiz number 1? Okay, I'll open this for you. No problem, I will open this for you. Okay, thank you. So basically, this is the superset of the course which is already offered by AICT, and the course name is Electronic Materials and Circuits. Electronic Materials, Devices and Circuit, that's the material. That course is offered as do I have 3 slides? Yeah, I have. So this course is offered as the minor degree course. So there are 2 terms. One is the minor and another one is honors. This is the new concept. Minor is the new concept. Honors is not new concept. Okay. So honors, I think there is some spelling mistake. So I think it will be like this. I need to check it. So honors is the old concept only. In earlier days, if your percentage was more than 70, then you were offered honors degree. But nowadays, since we have CGPA system, so definitely most of the class is more than 7 CGPA. So it is difficult to produce those many honors people in the same class. So what universities have done today, that they are going to offer honors or minor. For honors, you have to earn 18 extra credits. 15 to 18 extra credits are needed. Credit is what? We all know credit is against our subject. Generally, if it is 3 hours per week, that equal to 3 credit. If it is 4 hours per week, that's equivalent to 4 credit course. 2 hours per week is equivalent to 2 credit course. It is the simple thing which we used to have, but typically whatever we have covered, this is we have given it 40 hours, but this is equivalent to 3 credit course. This is what we have offered, right? So for honors, you have to take roughly 6 or 5 to 6 subjects you have to take into consideration if you want to earn an honors degree with your actual degree or the minor degree So minor degree is what? Let's say you are studying electronics and communication engineering, but you are very much keen that you should go for AI and data science. So the institutes are going to offer nowadays the minor degree in AI and data science, or it can be anything. Computer science. Some of them are interested because of this electric vehicles industry is booming nowadays. Solar cells are booming nowadays. So they are offering for electrical engineering. So in these, any of the student who is having, like in our institute, if we are having more than 8 CGPA, greater than 8 CGPA, then we are going to offer them in the 3rd year. They can opt for honors or minor. So for honors, 15 to 18 credits more they need to earn, and similarly for the minors, 15 to 18 more credits they need to earn. So if they are opting for honors, For example, one electronics and communication engineering student is opting for honors. Then honors, we will specialize. We have 4 branches in MTech. So according to any one of the stream, we will be offering. If the person is interested in VLSI design and technology, then we will be offering honors in that. This person will be offered honors in VLSI design and technology. So we'll be having 5 more courses for him, and those courses will be completed in 5th, 6th, 7th, and 8th semester. Those courses will be spreaded in this way. Likewise, for the minor degree, for example, let's say electronics engineer is interested to go for the minor degree in engineering physics. So he has to opt 4 to 5 courses, 6 courses in that particular stream. So this is about major degree and minor degree. Major, whatever you have been taken the admission, that is the major degree. That anyway you have to do. Okay, all these credits. For example, in our institute, it is 180 credit. Maybe in your institute, it can range from somewhere between 180 to 200 credits. In some of the institutes, in IITs, it is 160 credit to 180 credit. That's the range. In AICT institutes, it is typically from 170 plus to 200 for any BTech degree. So that's what they are expected to complete for a major degree, and then there is minor degree and honors degree. So whatever we have covered, this is actually the very basic course which is taught in our institute in first year and second year also. We have tried to make it to a little bit advanced so that it can help you in the research. So we have tried to make it a little bit advanced by adding this extra. This is one thing. This is the extra module, applications of diode and MOSFETs as sensor. And then other hands-on related to this. This is the extra module. Apart from that, whatever topics we have covered earlier, so we tried to make it in depth. For example, Professor Anand Bulusu on the first day and second day, he has 2 sessions. And in both of the sessions, he tried his best to cover it in depth. What is the Fermi level, how the Fermi statics is going to happen, donor and acceptor ions impurities, how the shifting of donor and acceptor ion impurity level is going to happen, how the EF, the Fermi distribution is going to help you, how the energy band diagrams are moving. All these things were discussed in depth by Professor Anand Bulusu, because we understand that most of you have joined this course especially for your research along with the teaching. Whatever you are going to teach to your BTech students, you have taken up this course for your research purpose and related things. So these things we have covered in details. In the PN junction diode, we have covered into the detail that how the electric field is going to form, how the electric potential and built-in potential is going to help the making the switch off till the knee voltage, then the peak inverse voltage and how it can be helpful to make a safe circuit. Like I told you, like peak inverse voltage is expected to be lesser than whatever the rating is. Sorry, your input voltage is expected to be lesser than whatever your PIV ratings are, so that your reverse bias of the diode is not going to increase from the peak inverse voltage and your device is safe. That we have discussed. Apart from that, we have discussed the Schottky diode. So in BTech level course, Schottky diode characteristics are shown only. So we have taken to the energy band diagrams so that you can understand, and it can help you in the research level if you want to prepare some advanced device in the listed softwares or whatever software you have with you. You want to prepare that, you can understand how the things are going to happen in the energy band diagrams and how the energy band diagrams is going to explain the IV characteristics of this particular device. We have discussed Zener diode avalanche phenomena into the detail, clipper clamper circuits, along with the cut-in voltage of the diode for the electrical and electronics engineers, especially we have discussed. Then op-amp and related circuits. Uh, so op-amp as instrumentation amplifier along with integrator, differentiator, simple circuits which are being used in UG courses that we have discussed. We have taken various signal generators and wave shaping circuits, including the sinusoidal waveform generation from the RC tank related oscillators and the LC tank related oscillators, along with the crystal oscillator. Then, apart from that, non-sinusoidal waveforms are being generated by multivibrators like bistable multivibrator, monostable multivibrator, timers, and a 555 timer IC we have used to create all those. So that topic is also being covered in detail. That topic was covered by Dr. Girdhar Gopal from NIT Patna, and Dr. Gaurav Datta from IIT Kharagpur, that was taken up in the detail. And yes, the whatever the note the professors have prepared, only one note is left that I'm going to upload soon. Others, I have uploaded all the notes received from all the expert speakers on the canvas. And yes, so these were the speakers. Apart from that, we have one more speaker. Two more speakers we had. Dr. Girdhar Gopal from NIT Patna and Mr. Amit Seni from Cadre Software Design. Yes. So if you have any questions so far, you may type in the chat box. We'll take the question, and after that we will proceed. That will make it whatever we have covered in the last 38 hours. We will be revising that so that you can brush up and you can recall what was actually covered in this. And if you have still any question, I'm ready to help you. So this session will be taking till 10 a.m. and after that we'll be having the validatory session. So do you have any questions so far? No questions? Okay. So now let's start with the first day presentation and let us revise it. What is the validatory? Validatory session means just saying vote of thanks. It will be just 5-10 minute session. Okay, saying thanks to all of you for your time and patience. Fine. Recording is already available. Yuvraj, recording is already available. Probably I have shared with you in your, yeah, I have shared somewhere. For the recordings, I have shared somewhere. So this is the learning skill repo. I have not pinned properly, but yes, I have shared. Let me share it again. Dr. Geeta, can you type in the chat box the link for recording? Anyway, it is there on the canvas also. Let me show you on the canvas. The link is already available over there, and this is, yeah, after the course, along with every session, we are putting the recordings. Along with each and every session, we are going to put the recordings. Yeah, these are the recordings. You have to go to the modules. Look at here on your canvas. Just below the quizzes, modules tab is there. Click on that modules tab. Okay. And when you will click on that, every recording is available. Day 1, session 1, day 1, session 2. There were 2 sessions on first day. Likewise, day 2, session 1. I can show you by opening any one of these sessions. For example, let me open this session. And likewise, this is yesterday's recording. One recording we are trying to upload is yesterday's session recording because it was evening and there was some more program going parallelly. So the people at the academy were a little bit busy. This recording I'm just opening for you the other one. So this is already available for all the 8 days, and today we are running on 9th day. So this recording will also be available after 10 a.m. And the day 8 session number 2 evening session, whatever hands related session we have covered, for that also the recording will be shared soon. Okay, so please try to explore the canvas. It is just like your Google Classroom, right? You will be having everything over here. I have not given you any assignment. I hope you have done at your own the practice questions and related things. Quizzes we have taken, fine, and we have taken also. So these modules are already available over here. And files, we have created the files. So for your use, these are the files. Lecture materials are the files for you. Okay, so you'll go to the lecture materials, and here everything is available. So please feel free to access it from here. And I request you, please download it. Although this session, this lecture will be there available, but I do not know, because of the memory issue or something else, maybe in future, after 1-2 months, maybe this can be removed from this particular cloud platform. So I request you to download whatever is useful for you. And yes, the YouTube sessions will be available over there. Whenever you need, you can just go through and you can take your whatever video lectures you actually want. Okay. So in day 2, what we have covered, the simple PN junction, how the PN junction diode is formed, and then the characteristics. So flow of charges, first of all, that contributes to the current. And we concluded that this is the equation. VE is equal to minus mu into E. This equation is applicable to every metal and semiconductor also. In case of semiconductors, this mu E will be replaced by mu N and mu P, because electrons and holes we are having two. So this is going to give us this equation for the current density. J is equal to sigma NQ into V, and from here we will be having the conductivity NQ into mu. That's the conductivity, and reverse of this is the resistivity. And from this we will conclude this equation, that is nothing but the Ohm's law. J is equal to sigma E is the Ohm's law. We have already taken up with the help of the derivation. Ohm's law is as such equal to V is equal to IR, right? So it is the Ohm's law. Then charge carrier conductivity for the metal, semiconductors, and the ionic materials. This is given over here. So ionic materials, especially in the batteries and all, electrolyte is there, right? So in that electrolyte, ions are also moving. If you can visualize that, yeah, you can visualize. You can just take a note. Ions are also moving. So these are the three things. First one is for solid metals, then for semiconductors, and ionic, especially for the electrolyte solution related things. The ions are going to move, like OH minus ions, H plus ions, and all, especially in your batteries and all. So current for the semiconductors, the current, drift current in the semiconductors is going to happen because in the own region, the current carrying phenomena in the simple semiconductor device is your drift phenomena. So there are two components of the drift current. One is the electron drift current and hole drift current. So we have taken both of these currents together if a particular semiconductor is there. So the current contribution in semiconductors is because of holes plus because of electrons. Since holes and electrons are of opposite charges, so even though these are moving in the opposite side, still the current is in the same direction. Electrons might be moving in this direction and holes might be moving in this direction, but still the current is in the same direction because electron is having opposite charge and hole is having a positive charge, right? Then there is another current that is because of diffusion. in semiconductors, the diffusion current because of n electrons and holes is given by this equation. So this happens, the diffusion happens because of the concentration gradient. Let's say you have a glass of water, this is filled of water, and you want to put a drop of juice or something. So this drop is going to disperse. It's going to take the place inside the glass. So that is actually your diffusion, right? This is the continuity equation that works on the conservation of charge. Whatever charge is coming inside this block, the same charge is going to exit out of that block. That is the continuity equation that's going to give us the details that in this particular time, how many electrons are being created and coming out of that black box. PN semiconductor we have gone through. So this triangle shape is P type and this uh, negative sign is N type, right? Then this PN junction formation we have completed. In the PN junction formation, basically we are having ions in the depletion region. So that's the depletion region, this portion, and this portion is depleted from the mobile charge carriers. There are two things. One is the fixed ion, this encircled in positive and negative, that is the fixed ion. And then this black color solid and the red color solid, these are the electrons and holes, these can move. These ions are very heavy as compared to electrons and hole mass, so these cannot move in the solids. But these electrons and holes are free to move because these are very lightweight and there is no nucleus attached with the electron and hole. So in this particular junction region, the electrons and holes are recombining all together, creating the recombination. And this region is depleted from the mobile charge carriers. That's what we call this as a depletion region. Now, if you look at this region is because this is your N type, this is your P type. Both of the sides you have heavily doped semiconductors or conductors, right? If you are increasing the doping, then the conductivity is going to increase, right? N Q into nu. So if N is going to increase, it means your conductivity is going to increase. Okay, I'm not able to type it over here. Yeah, I'm not able to type. So it means this is going to increase your conductivity. So I can consider that the left hand side and the right hand side, these are the contacts, and these in between the positive ions and negative ions are actually on those conductive plates. So it's like a capacitor, and whatever capacitance we will be having with the help of this, that known as the diffusion. So these are negative and these are the positive ions. On this plate you will be having the positive ions. Let me see if I have this in PPT format so that we can write it. I have to search maybe online or on other system that is there. Okay, so that was the session related to PN junction diode. Then the PN junction diode in the BTEC generally it is told, okay, the positive side the current is going to enter, and negative side the arrow says that the current is entering in this way, right? There is an arrow. This arrow says that the current is going to enter in this way. This is the way the current is going to enter. So this is connected to the positive supply and this is connected to the negative supply. These P and N regions are also termed as anode and cathode. As it was taken for the electron gun and related things, it was used in the literature for the vacuum devices and all. So from that it's been taken anode and cathode also. So that's similar to it, plus and minus. Okay. Plus stands for positive. Positive means you have to connect your supply to the positive. Negative means you have to connect your supply to negative in order to make this device on. Another thing, this arrow is synonymous to the P English letter. This is the P. P means ample number of holes. P type region, that's going to tell this arrow. And this N type, like this N is taken up. This N will be in this way, right? So this N is taken up, and that's what it is going to tell you, that okay, this is straight line is equivalent to your N, and this triangle shape is equivalent to your P. This triangle shape is equivalent to your P. Now, with the help of these energy band diagrams, energy band diagram is one of the key parameter if you are working in the device to circuit or device to any of the application. You should understand the theory behind energy band diagrams, and I hope this course is going to be very helpful for those who are working in the physics related to the devices and all. So how the energy band diagrams are formed? First of all, if you have multiple dissimilar materials, what we have to do, we have to align the energy band diagram first of all. So you can see we have N type and P type. Let's say this way, this is N type. So this is, we know the Fermi level will get shifted towards conduction band for N type. And for P type, the conduction band is away from the Fermi level, or I can say the EV band. The below one is the EV band. This is much more near to the near to this Fermi level. Then what we are going to do is we are going to align this. We are going to align this. So this is the aligned manner. If we are going to align this, then on the junction, see, away from the junction, that's the steady state. This is purely P type. This is purely P type, and this is purely N type. We can visualize from the energy band diagrams, right? Yes. Now the things are going to happen at the junction. This is the junction. So at the junction, we have to make the vacuum in the continuous format, and that continuous format is going to make the changes in the conduction band and valence band, etc. So this conduction band and valence band you can visualize over here. This is taken up in this way. So basically it is going to take the shape of a parabola. Why this is going to take a shape of parabola? Because we are going to solve the Poisson's equation, and Poisson's equation is having the second order equation, right? So if it is second order equation, its output will come like x square you will be having. In the output, x square you will be having. So your equation of parabola is, or a standard equation of the parabola is, means you have x square in the standard parabolic equation. Any second order equation, you can say that this is parabola. So yeah, so these are the energy band diagrams when we are making the junction in the forward bias, reverse bias, and the middle one is actually the equilibrium. You can see the EF level is aligned for this complete. This is the EF level. Then if you are making it forward bias means P is connected to the positive. So what we know, the work done per unit charge is V, right? So W is equal to minus QV, that's nothing but energy. So if you are applying the positive voltage, this is going to downside. That's why this EF level is going to downside. So let me tell you one trick. If you are going to draw these energy band diagrams, so whatever potential profile you want to draw, make sure your EF level is just reversed. Means you just check your EF level, and that is going to represent the EF level, the Fermi level. Actual Fermi level is going to give you the potential profile of your system. Okay. Yes. So in the negative side, this will go up, and you can visualize over here, this depletion layer has been increased, but after some time you will be seeing that this width is getting decreased. and the electrons will be able to cross this barrier because of the Zener tunneling phenomena if it is degenerately doped. So this is for the biasing we have taken up. We can visualize from here that these are positive and negatively charged ions. So these ions, when you are going to write the Poisson's equation, you will be writing the equation separately for this portion, positive portion, and for negative portion, like p side portion, you'll be writing separately. So this charge is equal but in opposite side and opposite in manner. So because of that, you will see that there will be one electric field generated, and that electric field will be converting to the electric potential. And because of that, finally, you will conclude that there is the current equation I is equal to Is exponent of Vd upon Kt by Q minus 1. So Kt by Q can be represented by Vt, that is nothing but the thermal voltage. Is the reverse bias saturation current that is measured in nanoamperes or maybe microamperes. But the forward bias current is measured in milliamperes for this device. This minus 1 says that this was the diffusion current, reverse bias current. So the reverse bias opposes the forward bias. So in the like this current is because of the drift. This particular current component is because of the drift that is in the diode on direction, and minus Is is in the opposite direction. So these are the IV characteristics of the Zener diode. And for simple diode, the characteristics will be similar, but the breakdown is going to happen in this way. And we will be calling that as PIV. PIV. And yes, we have to avoid this region. This is the avalanche breakdown region, and we are going to avoid this particular region. So in a circuit, how you will be utilizing the simple diode, this is shown that you have to, for sure, you have to make sure that there is one uh, series resistance connected to the diode. And this series resistance is basically the safety resistance, so that the excess current, because we know that the forward bias diode, how much current it can, how much voltage drop can be there in the forward bias. Can you type in the chat box? Maximum amount of the voltage drop in the forward bias. So there is a question, what is the charge of P or N type semiconductor under no bias? So for semiconductor, there is no charge for P type or N type semiconductor. This we can explain with the help of charge neutrality condition. Let me take a blank slide for this. Yes. So basically, when you are having, let's say it is a P type semiconductor. So what are there in P type semiconductor? You have acceptors. Acceptors like boron, aluminium, gallium, indium. All of these are from group 13 or group 3. In the previous days, it was told that this is group 3, but according to the new periodic table, it is told that these are group 13 elements. So the old textbooks are still referring, even the higher education textbooks are referring it to group 3, but nowadays, because the next generation is coming and writing the books and all, so now this is the same thing. Group 3 element is nothing but the group 13 element. So group 3, the name was concluded that it is from the point of view that there are maximum 3 electrons in the outermost shell. And the group 13, it's been taken up nowadays according to 1, 2, 3, 4, 5, the complete, it's going to take the complete number, and then it comes to the 13. In between, the other 10 numbers are being adjusted, which are from D category, I believe, right? So this group 13 will be having 3 electrons in the outermost shell. For example, we are talking about aluminium. So in order to make the structure stable, what it needs 8 electrons. But aluminium is only having 3 electrons. Other side, the silicon elements will be there. So the doping means only a few aluminium atoms are there in the complete structure. So this is going to be helpful to tell that, okay, this aluminium is having one hole. Basically, it is going to have one hole. Let me change the color to tell that there is one vacancy. So this, let's say this is the vacancy. So what it is going to do is, if we are having some greater temperature, there are free electrons and holes. So I hope you are able to see these dotted line, dotted and the blanks. So these are holes and these dots are electrons. So these holes in electrons will come from intrinsic behavior of the semiconductor. So when no doping was there, there were at room temperature approximately 1.5 into 10 raised to power 15 atoms per centimeter cube in silicon. I'm telling for silicon, for different materials, this value is going to differ. So these many atoms are existing, which are electrons and holes. These have been created because of thermal vibrations, thermal energy. Okay, thermal energy, and then the electron hole pair generation took place. So electron hole pair generation took place because of the thermal agitation in the this particular material structure. Fine. So now this particular, this one, it is going to take up one electron out of these free electrons and it is going to make its bond complete, right? So what is going to happen, one electron which is taken from the material structure, and this is occupied by this aluminium. So for silicon it is fine because it was contributing one and it is expecting one, so silicon will not have any charge. But the aluminium, it is having, how many protons are there in the aluminium? Can you help me? Can you type in the chat box how many protons are there in the aluminium nucleus? 1, 2, 3, 5, 10. Can you type in the chat box how many protons are there in the nucleus of aluminium? So it is 13 number, so it means 13 protons are there. But how many electrons now? Because of these 3 electrons of its own, it was having 13 electrons. But now one extra electron on behalf of aluminium, because of the stability of the structure, has been occupied from the material space. So that's what one more electron is being added to aluminium, right? Now this is negatively charged particle. Please make a note, it is negatively charged particle now. Devasis, can you hear me? Now this is negatively charged particle, and this negative electron, from where it came? It came from this free space. It is not free space, material free space it came. Okay, so what was the total material before aluminium? You were having, let's say this is your silicon, which is at room temperature. So you are having electrons is equal to Ni, concentration of electron. That was, let us roughly conclude, 10 raised to the power 10. And the same number of holes were there. Now what you are going to do, let's say I am having aluminium acceptor ions, Na is equal to 10 raised to the power 15. So these 10 raised to the power 15 are going to be spreaded over here. And of course, what these are going to do, these are going to occupy the electrons from the free space, right? So basically, the electron concentration is going to reduce. How this electron concentration is going to reduce, that we can figure out from the mass action law. Np is equal to Ni square. So the number of these fixed ions, these are the fixed ions, right? Plus the number of minority carriers electrons, right? That's the same equal to the number of holes available in this free space. Okay, so if we are introducing aluminium, basically holes are going up. So it means electrons are reducing. Electron is negatively charged particle. Okay, so let's conclude it over here. Aluminium negative ion. Okay, the number of aluminium ions are increasing. It means the electrons, free electrons available are decreasing. And there were holes available, and both of these are equal to the number of holes available. So holes are increasing if aluminium is doped and the electrons have decreased. So there were some Ni already holes were there. These holes will actually be increasing, and both of these are actually opposite to each other. So the total charge is 0. If you see any semiconductor, so the total charge is equal to 0 under no bias conditions. Please make a note. Total charge on this particular N-type or P-type semiconductor is 0 under no bias conditions. And for metals also it is similar to that. Let's say you have a metallic bar. Fine. Let's say we are talking about any metal. Let's say let's say you are having gold. Au. So Au is going to give up one electron. If it is going to give up the electron, it means it is positively charged ion. And that electron is there in the free space. So the number of electrons in the free space is equal to the number of gold charged ions. The number of gold charged ions. So basically, this is the electrical neutrality equation that we have already discussed. Always it works on everything. The number of positive ions or maybe the charges is equal to the negative charges. So when we are talking about the charge neutrality, we have to take into consideration mobile plus ions altogether, because both of these are charged particles, right? Both of these are having charge, whether it is fixed ion or mobile charge. But when we are talking about the current conduction under the biased condition, what we are going to have is we only look into the mobile charge carriers or electrons or holes. Okay. Okay. So now let's proceed. So those who are working in devices, it is very much needed that first of all you should understand the basics of MOSFET and diode, and derive the Poisson equation and whatever related things are there. In Millman Helkia's book, that is covered the diode and related equations for the energy band diagrams and everything, that is covered in much more detail. Even the Fermi direct distribution also in Millman Helkia's book, that is covered in much more detail. So refer that book, and approximately 4 to 5 chapters of that book will actually make you good understanding about it. First 4 chapters you can take and last 2 chapters you can take. That is more than enough for the device. And for circuits and others, you have to go for the rest of the chapters. We have discussed the heterojunction device also. Why the heterojunction is relevant? See, when we are talking about silicon, so for the advanced devices, like in yesterday's lecture, we have discussed, like if we are talking about uh, silicon with tunnel fat, so the own current is very small. It comes like in some microamperes with SiO2 as the gate oxide. So it means we have to discuss the heterojunction, right? Heterojunction is utilized in different applications. For example, LED is because of the compound sim. There are two things. One is the compound semiconductor and then heterojunction. So there are different applications. So LED is generally made up of gallium arsenide. Okay, and then the variants will come if you are changing the percentage gallium phosphide you are preparing. You will be having a different kind of LED structure, light emitting diode. So the light emitting diode becomes because the energy, there is a direct and indirect band gap. So silicon is the indirect band gap semiconductor. So what you have to do is you have to create the direct band gap semiconductor. You have to make a direct band gap semiconductor with the help of which you can create the electron from this can actually come to the valence band directly by releasing its h nu energy, that nu actually in the visible spectra. Okay, so in the heterojunction, especially how this band bending is going to happen, that is governed by Schottky-Mott law. So first of all, we will make the Fermi level equal, right? After that, we'll make the because of the electron affinity, we will be labeling the vacuum level. And then since the vacuum level and the Fermi level at the junction, these will be differing, right? So at junction, we will be making a sharp change in the IV, these EB band diagram curves. So we have discussed the Schottky diode, which is nothing but a metallic junction and the semiconductor are connected all together, and that this particular slide shows how this is being converted to the, see, this is away, the conduction band is away from it, so it will behave like the p-type semiconductor, although this was n-type semiconductor, but at the junction there are ample number of p accumulation has happened in this particular biasing, accumulation has happened over here. In this particular case, in this particular biasing, you can see the EC is moving towards the EF, right? That is going to give you the rise number of electrons at the surface level. This is the surface level. So rising the number of electrons means you are going to make it inversion channel type. You are going to create just beneath the surface line. So the characteristics of the Schottky diode and the applications. So you can see the shift in the characteristics. The cutting potential of the Schottky diode is considered to be 0, and the off current is much more. And these are working at high frequency applications and very fast switching speed. Next, Zener diode, especially it works like the diode regulator. So these are the different regions of operation for the Zener diode we have taken into consideration. Off current, and then it works like the constant current source. Sorry, constant voltage source. So the constant voltage source uh, means the internal resistance of that voltage is 0. So the current is internal resistance is 0. It means V divided by 0, infinity current. So the current will be controlled by the outer circuit, which we have taken up with the help of the Q point concept, right? So these are the energy band diagrams. We have already discussed about this. And we have taken the Zener diode as the load line regulation. Load line regulation means you are going to vary your load. So you are going to determine that what should be your RL minimum and beyond. Likewise, there is line regulation. In line regulation, you are going to change, your input fluctuations are going to change, and what minima and maxima can be achieved for that, that is discussed. Then the very first application we have discussed the half wave rectifier and full wave rectifier with filter. So when you are just applying the filter, you will be seeing that this actually is being converted to a little bit much more near to DC. Ripples are reduced if we are putting up the filter. So this is the full wave rectifier, the center tap and the bridge rectifiers we have covered. So we have discussed that the peak inverse voltage in the bridge rectifier can be seen twice of whatever we were seeing in the center tap rectifier. The reason being there are two diodes in the bridge rectifier. So those two diodes means the reverse bias voltage will actually be divided into both of them. That's why the PIV ratings can be taken up, just double of that. We have discussed the diode clippers. Clippers means clipping the portion of the circuit away from it. Diode clipper means clipping some of the portion. For example, this is 5 volt, and this 5 volt is going to support the forward bias of the diode. So what will be the output? This 5 volt 4.3 volt, because 5 minus V gamma, right? We have already discussed that. So this will come V in minus, yes, V in minus 5 volt plus V gamma. Let me take it V gamma for G, and that is equal to Vd plus V out. So of course Vd is equal to 0 when it is this particular thing is greater than 0. So Vd plus V out we are expecting greater than 0. So we'll make this whole quantity greater than 0 and find out your Vd. Okay. So V in is expected to be greater than 4.3. This is V gamma was 0.74 for this particular category. Yeah, oh, I have taken it reverse. So this is plus 5 volt because plus the battery of minus sign is seeing the positive sign of the input voltage, and minus the diode will be 0.7. So if we will take this inequality, it's going to give us V in is equal to, yeah, V in is greater than equal to 4.3. It means 4 point minus 4.3. If V in is minus 4.3 and more than that, that means your diode is going to become on. If the diode is on, then the complete voltage, this complete is going to appear at the output. So this will be equal to your VO with this, the below condition, and rest of the portion is cut away. So this is the diode clipping, means you are going to cut down the unwanted potential, unwanted waveform. Whatever unwanted waveform is there, you want to cut down that. Next was the clamper. So clamper is the circuit which is going to change the DC level of your device. How the DC level is being changed? So the DC level is changed by introducing a capacitor. This capacitor is going to work like a battery. Am I audible? Please type Y in the chat box if you can hear me. Or if you have any question, you please feel free to type. I will take the question. So diode clampers we have discussed, and now let's take the MOSFET related portion. So this the very first lecture was related to type of materials. So type of materials are multiple types, but for electronics purpose we'll be taking 3 types of materials. What are those? The 3 type of materials we'll be taking into consideration: metals, semiconductors, and insulators, right? I have discussed the market and applications of VLSI and related courses. So the applications related to this we have discussed with the help of the consumption of mobile phones and laptops in the Indian market and worldwide also. So we are having approximately 140 crore, we are having the population, and the world population is approximately 800 crore. So approximately we are having 1/6 of the world population. So with that figure in the mind, and another thing is we are youngest country in the world. Youngest country means young people are consuming more. So it means the market in India is more. So it means there are much more jobs in this particular market. So pay and perks, very good payouts are there in the VLSI industry. Materials we are going to use are 3 materials: semiconductor. Yes, sorry. So we are taking the materials: conductors, semiconductors, and insulators. These 3 materials are of our use. There are different materials for different applications. For mechanical applications, something different. We know electrical properties will be looking in this particular case. Electrical properties are resistance, capacitance, electric field, voltage, current, all these things. We have discussed how the band formation is going to happen. So what is going to happen? Atomic scale was there. So in atomic scale, all these levels were actually the discrete levels. If we are decreasing the distance between 2 of the atoms, so then these are coming all together, and these are settling down over here. And here you can see this is actually the filled state energy band, blue color, and this uh, yellowish color is empty, see, conduction band, empty states band is there. So these are forming a bond. with bands. The energy bands are creating the energy discrete levels are creating a band, and that's what the formation of the energy band is going to happen. Okay, so generally this phenomena, please try to make the students understand in a good way. Most of the students I have seen in the private colleges, whenever I am visiting, I have seen that they are not aware about this phenomena. So please enlighten that about this phenomena in the very first or second year of their classes. So based on the energy band diagrams, these are the band structures of the different materials. So in case of insulators, the band gap is too much that the electrons from valence band cannot jump to the conduction band. They can never have that good amount of energy. Okay. In the semiconductors, the band gap is good enough that the thermal excitation or some other energy, if it is being applied, the electrons can come out from their filled states in the valence band, and these can jump to the conduction band. And likewise, the conductor is there. Conductor is having no energy band gap. So means valence band and conduction band, both of these are overlapping. This is the structure. In this, you can see outermost is having 4 electrons, and other 4 electrons are being shared by the other nearby silicon atoms. So it is kind of like sharing and caring kind of structure. This is the energy band diagram. Direct band gap means the minima of conduction band is seen at minima of the valence band. So we'll call this as direct band gap. And the other one is the example of indirect band gap. So silicon is coming into the indirect band gap category. In this, there are defect states or the trap charges. Through that, the electron is going to come from conduction band to the valence band or vice versa. These are the EK diagrams. So K is the wave number, and this wave number is actually a parabolic function. This E is a parabolic function actually. So you can see K square is coming over here. So if you are writing the EK diagram, so this is going to take the parabolic shape. And these this K number, pi by A, twice of pi by A and all, these are going to give you the different Brillouin zones. So yes, this is the diamond cubic crystal structure, and based on that, we'll be having different planes, and the crystal structures related to that Miller indices are one, which are going to give us the information that how your cubic planes are placed. So 111 means you are taking it the crossing of your cubic plane at 111 x, y, z axis of all these axes. You will be taking the intercepts and reverse of that. Those are the Miller indices. So these are related to the direction cosines. DCs are there. So somehow these are related to that. So intrinsic semiconductors is represented over here. EF is there in the middle of it, and then the conduction and valence band are directly away from this. Extrinsic semiconductors will be having the EF shifted towards upside for the conduction band in N-type, and P-type it is shifted downside. So silicon behaves like insulator at 0 Kelvin temperature, and at room temperature it is semiconductor, and it is conductor if we are doping it. So this was discussed related to the basic semiconductors. Now let's take the, I will be doing it quickly. We are having just 20 minutes. By that time, if you have any question, please feel free to ask. If so, we discussed the op-amp in our 6th May lecture. So op-amp is one of the very much useful block in the various applications, starting from the logic operations to ADC, analog mixed signal IC design, various logical operations and various amplification purpose we will be depend on op-amp, operation amplifier. So it can perform various operations like this is inverting mode, non-inverting mode, adder, subtractor, integrator, differentiator, etc., etc. So This is actually the four-state op-amp. Four-stage op-amp 741 IC diagram. First two stages are there for uh, amplifying the gain. Because both of these are cascaded, so the gain is being multiplied AB1 into AB2. And then the third one is the level shifter, and there is last one is the output. That is the output stage, which is going to offer the low output resistance. Then this is the op-amp 741 IC. With the help of this IC, will be this IC is available in each and every college and lab because this is very much cheap. So we can utilize that IC. Also, I will request you, all the faculty members and researchers, when you are dealing with the labs, try to use breadboard instead of ready-made kits, because the students will be able to learn more with the help of breadboard and the related connections with the ICs and all. So this is the internal diagram for the op-amp, and we can see this Ri is very high, so we have taken it infinity. So it means very high means no current is going to enter into the op-amp, and output resistance Ro is almost equal to 0, that is assumed to be very low, and that we have taken with one example, and we found that this without considering R in very high 1 mega ohm and RO is equal to 50 ohms, we are coming to this particular figure, but minus R2 upon R1, which we'll be taking in this particular example, that we are reaching to, yes, that we are reaching to the same number 4, right? So 3.99 is much more near to 4. So we'll be taking in all the calculations, we'll be taking the two formula, inverting and non-inverting amplifier. There are two formula. One is minus RF upon R1, that is for inverting mode, and for non-inverting mode, we'll be having 1 plus RF upon R1. So into V in. So V in is whatever voltage you are going to apply over here. So voltage follower is generally used for the isolation purpose and the buffer circuits. When you will be doing various kind of projects, generally this buffer stage is very much needed, because most of the bigger project circuits, those are not working, although those were working individually. So in that case, you have to apply some buffer, and this buffer is going to create the input and output circuit isolated to each other. This circuit 1 and circuit 2 are isolated to each other. Then there is non-inverting amplifier. So if this non-inverting amplifier is going to give you 1 plus RFB upon R0, where this is the non-inverting terminal where you are going to apply your voltage. Yes, common mode rejection ratio is very much important parameter. Apart from this parameter, there is offset current, yes, bias current, offset current, slew rate, PSRR, power supply rejection ratio, and all. Difference amplifier we have discussed, where V1 minus V2 we want to find out. So here we have used two things. One is the inverting terminal and the non-inverting terminal also. After this, we have discussed the uh, INA also, instrumentation amplifier. So this instrumentation amplifier is utilized to remove the noise if it is there in the input signals. That noise is removed with the help of this instrumentation amplifier. This instrumentation amplifier is very much useful in your sensitive analog circuits. Yes, so yes, we have completed this. We have completed this day one also. So the next one, yesterday we have covered various devices, advanced devices, which can be very much helpful topic for you as as a researcher, or maybe if you are in third year or final year or in MTech, you can take up any one of the device and you can do the analysis. That will be really very good project for you. Final year project, generally our students are doing that, MTech students are taking up, and the PhD research scholars are taking in depth. So this particular lecture probably has given you the insight about how the things are going to happen, starting from MOSFET, how you are going to shift to FinFET and all. So this slide tells that being a device electrical engineer, you should also have the knowledge of various materials, semiconductor processing, semiconductor physics, and then you have to apply that into the circuits, information, and theory coding. So Moore's law was there since years, but Moore's law actually the scaling started to fail down when we were reaching to much lower technology node. So we came to the Moore and more than Moore era, right? So that is means this is for Moore and more than Moore and beyond CMOS devices. So yeah, so Moore means baseline CMOS roadmap was in this way. It is shown over here. It means we switched towards FinFET side. Then more than Moore means we have switched towards the MEMS and related applications. So you might have seen when the BTech students are going to do some Arduino based project, they are designing some prototype which requires some, let's say, some motors, tiny motors or something like that. Those are prepared with the help of MEMS devices. So small gears, very tiny gears, very tiny motors, where the mechanical thing is also going to happen, and they are putting that in the Arduino circuit and all. So that is created with the help of MEMS and NEMS. MEMS and NEMS are similar. The only thing is there is a change in the dimension. N stands for nano electromechanical systems, M stands for micro electromechanical systems. And there is another concept like flexible electronics. Flexible electronics means just you can fold it just like a piece of paper. So the electronics can be drawn on a piece of paper. So when I was there at NIT Trichy, I conducted an experiment. So it was related to preparing the capacitor, parallel plate capacitor as a sensor. How they have prepared it. I hope you can also take that for your students in the class. So they investigated that the ink, uh, if they are using some conductive ink with some glue they have used, and that was actually can be pasted on a piece of paper or maybe paper glass or somewhere else. So it will become the parallel plate capacitor. For example, let me give you the insight what we have done. So let's say this is the paper glass, and one portion, let's say this portion of it, half of it you have pasted the conductive ink. Okay, so let me change the color. Half of it is pasted with the conductive layer. So since ink can be pasted easily, they have pasted it. Keep a small gap and then paste it in this way. Okay, so this actually is a metallic plate and this actually is a metallic plate. You can put inside anything. In this, you can put anything, and that anything actually is having some epsilon. If this epsilon is getting changed, it means your conductance is getting changed. And you can utilize any of your analog circuit, which is easy to visualize, and you can find out how much epsilon has been changed, hence the capacitance has been changed. Okay, the same phenomena you can connect with your MOSFET device or like maybe the diode device, so that you can visualize that how much is the capacitance change. What various applications I have done. I during my tenure at NIT Trichy, my students, I have taken 1 to 2 hours session for them. Okay, how they are going to create it. See, we have to put the brainstorming for the students. Students can do the experiment, but they need the guidance, right? So I told them the various applications. For example, I told them counting a bundle. Let's say we want to count a bundle, that how many papers are there. Let's say we want to count how many notes are there. So the capacitance will get changed. You can roughly figure out that how many uh, papers layer of papers are there. Just apply one conductive layer on the top of it and one conductive layer on the bottom of it. Connect and find out connect this capacitance to your circuit to figure out how much capacitance is there. So my students have utilized directly the capacitance measurement with the help of this multimeter. So multimeter is very low cost device. Even students can purchase it. Is costing about 500 to 1,000 rupees for the personal utilization. In lab, you can have the costly multimeters. So that would be okay. It can measure the capacitances, and that change in the capacitance actually is directly telling you that how many layers of that particular epsilon material were there. So that is directly related to epsilon ox upon T ox into the area. So see, T ox is getting modulated if you are increasing the number of layers. Let's say these are the paper layers. Paper means I want to count how many nodes I have in one particular bundle. So I can utilize that. Now we have taken some edibles also. For example, in mostly honey is there in the market, and honey is actually having adulteration with jaggery. That adulteration is going to means we are paying for honey that is very costly, but we are getting jaggery. So if this adulteration is not admissible, so that can be figured out with the help of this type of a structure. These type of things we have taken in the class in the similar electronic devices and circuits was the course second year, third semester, in which I have taken up these type of experiments with that. So basically we have MOSFET. From MOSFET, we are switching to FinFET because there was a problem that the gate control was losing down when the technology scaling was there according to the Moore's law. So this comes into the category of more and more, and we are having the multi-channel control. So if this control is on two sides only, we call this as double gate. Okay. If this fin is presented in the cylindrical format, let's say this is the cylinder. In this format, this is created, and all around this you are having the oxide layer, and yes. So all around this you are going to have the oxide layer. I wanted to change the color. This is the oxide layer. On the top of it, you are having the metallic layer. So that is the gate all around. That is just the variant of the FinFET. Okay. So gate all around means instead of two sides of this fin, you are going to control from all sides of that particular uh, cylindrical channel. So that is much more control as compared to the FinFET. So gate all around is one of the topic which is going to come into. Yeah. Now we discuss about what are the problems with the planar MOSFET and what are the solutions to it. So planar MOSFET was having basically two NPN diodes back to back connected are prepared, kind of Darlington pair kind of structure is prepared, and that is responsible for the multifold leakage. And that leakage is actually power dissipation, unwanted power dissipation is going to happen because the complete power we are getting from somewhere in the from the supplies, and that should be utilized by our circuit. So the leakage is unnecessary loss. Right? So in this particular diagram, the next diagram, we have utilized the partially depleted, and the next one is the fully depleted. Fully depleted is for very thin active regions, and partially depleted for a little bit more active regions. It is shown over here, partially depleted and fully ultra thin and nano SOI depleted is shown in this particular diagram. Then this is the FinFET structure. In this FinFET structure, let's say you want to take this as a project. So what kind of research you can do? You can actually make it underlap, overlap, and normal comparison of these. Underlap region means the channel region, whatever you have selected, you will be taking three variants that the complete channel is let's say this is your N plus region, N plus region. So if you are taking your gate oxide over here and putting your gate over here, this and this region is not covered. So this is your underlap structure. This is your underlap structure. Overlap structure means your gate is occupying some of the portion towards drain and source side also. That is the overlap structure. And in the simple yes, normal structure means just like this. Normal, just aligned with the channel you have. So this is one category. Another category, you can find out the temperature effects. So in the simulators, you have the facility to put the temperature variations on. And let me tell you, we have discussed the cadence hands-on. We have given the cadence and visual ticket hands-on. In that also there is the facility in cadence, there is a facility to find out the process parametric variations and the temperature variations, and you can find out the results, because in the fabrication all these parameters will be taken up, right? हाँ नमस्कार सर. हाँ सर. हाँ आप कर लीजिए ना सर, 1 मिनट के लिए ज्वाइन कर लीजिए. अच्छा ठीक है सर, ठीक है सर. हाँ ओके सर, थैंक यू. डॉक्टर गीता. यस मैम. Yes, Professor Sabula was about to join. Please try to connect him. He is going to be presenting the validatory session. Okay, ma'am. Sure. Yes, by that time, let me explain them, the devices, advanced devices, and related that. You can stop me, please. Whenever he is going to join, please stop me, okay? Yeah. So, yes, the need for FinFET we have already done. I hope I am audible. Was it disconnected? Hello. Hello. Yeah. So one of my PhD scholar, Dr. Rashi Chaudhary, has taken up this dual material. This is a dual material gate, gate 1 and gate 2. And she has studied how the things are going to vary. She has taken the SOI structure, fully depleted SOI structure. In that, she has taken into consideration how the temperature is going to impact the various things, and how this double material gate is going to reduce those short channel effects. Short channel effects are just like your DIBL, drain induced barrier lowering, gate induced barrier lowering, sub threshold swing, and yeah, punch through, pinch off. These are actually your short channel effects, and we can say the second order effects. Some of them are the second order effects category. So these we need to take into consideration if we want the actual performance of the device. So I have taken this from her work. This was for dual metal gate. So for gate 1 and gate 2, you can visualize over here. Simple metal, one gate was having much more high electric field, and the potential profiles you can see from, you can visualize from these two diagrams. So the first one is for, this diagram is for double gate, double metal gate, and this is for single gate. These are the potential profiles, and these are the electric field profiles. So the electric field profile, if you can recall, drift velocity was equal to mu e. That was the drift velocity of the electrons. That was directly connected to electric field. So if the drift velocity is going to increase, the electrons are bombarding at the drain with much high speed. That is going to create the structural problems in the device, and the temperature in that particular area is going to increase. That is not really good for the health of the device, right? So if you have any questions, so these type of things we have done, and you can follow my papers. If you have any issue, I'm ready to help. So apart from that, we have discussed tunnel fat also in detail. Yeah, so that's it. That's what we have discussed. So if you have any query, please feel free to ask. Otherwise, we will go for the conclusion of the session. If any one of you is interested to speak up, we'll give you the mic permission. Dr. Geeta, can we give them the mic permission if some of them want to speak? Can you hear me, Dr. Geeta?
Yes, ma'am. Yes, ma'am. But we cannot unmute them. They can type only, ma'am.
Okay, okay. So please type in the chat box. We are open to the discussion. Which one is superior? So it depends on the application, Devasiji. It depends on the application, that what is the application you are looking for. For example, if you are looking for sensor application, so for this also, you can go with some of the papers which Dr. Shalini has explored for the analog and digital applications. So for analog applications, there are certain parameters. For digital applications, there are certain parameters. What you have to do, Dr. Geeta, Professor Saula has joined. Please connect him, make him panelist.
Okay, ma'am.
So basically, tunnel FET and FinFET, it will be depending on your application, that what is your application, depending on that, you have to choose it. It can be like, first of all, with the help of simulation, you will be finding your device parameters, analog parameters and digital parameters. You will compare those parameters and then you will conclude whether the device is good for that particular application or not. Typically, tunnel FET is used for sensors, and FinFET is for circuit applications and memory applications is typically used. Devices. Any other question? If someone is having any more question, please feel free to ask. No questions? So we have Professor HAZ at Electronics and Communication Engineering Department, and he is looking the EICT Academy. He is the Chief Investigator of EICT Academy project at MNIT Jaipur. He has joined this validatory session. So I request Professor Sahula to say few words and concluding remarks about this session. Thank you, sir.
Yeah,
Can you
thank
hear
you,
me, sir?
Doctor. Yeah, I'm here. Am I audible?
Yes.
Good morning.
Yes, sir. Yes. Yes,
Yeah,
sir.
thank you,
Good
Dr.
morning,
Menka.
sir.
Good morning to all of you, the participants, our team here at AICT Academy and Dr. Menka. And I think it's time to thank all the speakers and the participants for making this a good event and successful event that way. And I hope all our participants will actually spread this kind of a pedagogy for this field, semiconductors, so that our ecosystem in India is strengthened for the semiconductor manufacturing as well as design. I have not much to say. Only thing is I can say that this is one of the program in the series of 4 or 5 programs where AICT has given us a kind of a guideline to all of us under the NEP 2020 that every institute is now free to offer the minor program in VLSI design. And AICT has prescribed about 4 to 5 subjects as a subset of VLSI design domain, which these BTech courses, we can include them and award the minor degree along with the other major degree of electronics or electrical or computer, whatever. So this is was very first of the program in that series. 4 programs would follow. Another program will, I think Dr. Menka can enlighten us. Another program by her is on VLSI testing and testability, maybe in June, July. And we have one on design verification in June itself and 2 more down the line. So if you are interested, please join those programs also so that you can strengthen the strength that your own institute and your institute is actually empowered to offer those courses, and your faculty can teach them. Um, we also have an offer that if you attend all 5 courses, we'll give you a PG certificate saying that you have done equivalent of 15 credits in this domain, which will remain with you as uh, a kind of an endorsement that you have gone through a specialized series of courses that way, which might be beneficial for your professional life later that way. So I again thank all the speakers, thank Dr. Menka for tremendous efforts, thank my team of Dr. Geeta and Ramesh, Deepesh and Manish here, and all the participants for joining this program. And I hand over it to Dr. Menka for further processing. I think we can invite the individual feedback from participants. Apart from that, we can have some testimonials just now only, what people have to say about their suggestions about improving this program, or what thing they have liked, so that we can strengthen that aspect of the program. Both ways it is invited. I think Dr. Menka will take over that way. Thank you very much.
Thank you so much, sir, for giving us this opportunity to connect with the faculty, which is going to empower our upcoming engineers in this particular field. And I got this opportunity through EICT Academy Amenity Jaipur, so that I can get connected with the future of our country. So the future is in your hand, and you have to spread a word to your students that how they can be much more employable in this particular field. We have during Corona, the world has seen the semiconductor chip blackout was there, and because of that, the many of the big business people were actually not working really well. So if we are having in-house facility, it is definitely going to give us added advantage. So I am very thankful to all of you. You have joined this course, and as sir is going to tell that we have a series of programs. So we are having upcoming program that is design verification, which is coming into the June. After that, there is VLSI testing and testability. That is according to the whatever minor degree they are going to offer. AICT is going to offer minor degree in VLSI design and technology. That's there in July, second week of July. We will be having the advanced version of this semiconductor devices and all, specifically for the researchers and all. That will be there in June. That is in the pipeline. So you may register for that also. And a series of 5 to 6 programs listed by AICT we will be having, as sir is suggesting. We have the option for the PG diploma certificate for those faculty members, and you can run that program at your institute. You are eligible to run those minor programs at your institute. So thank you so much, sir, for giving us this opportunity. I'm very thankful to all the speakers who have taken time out of their busy schedule. I'm thankful to Dr. Geeta, Deepesh, Ramesh, and Manishji for their unconditional help at any point of time. If I have some problem, they are there to help me. So I have seen they are working till late night in the academy till 9 o'clock. Some other course was going on, and they are still working day and night. They are going to work. So thank you so much, all the participants. If you have anything to say, you may please type in the chat box. Any testimony or something?
Yeah, Dr. Menka, we can even unmute them, and they can have their video if they want to share their feedback.
So Dr. Geeta, can you please help us to unmute them?
I will check because once we created this, we didn't give that option. I'll try. Otherwise, they can type in
Yes,
the.
please. So I have
Mean,
shared the feedback form also over here. I request all of you regarding this course. It is going to take just 1 minute. Just submit this form. This will be helping us to further delivery of this particular such type of courses. Thank you, Devasisi. Thank you so much. One more thing.
yeah, please go ahead. I have just one slide to show where the all programs are displayed. So I will just do it after your discourse.
Yes,
No
sir.
problem.
Yes, sir. So if some of you have not gone through quiz 2 or quiz 1, please take that quiz, because while releasing the certificates, we will take into consideration the quizzes and the attendance also. So yes, yes, sir. Please, over to you.
Yeah, so just for the benefit of those who haven't gone through the AICTE document for minors in BTech, the scheme is you have a major in BTech, maybe electronics, electrical, or computers, and the electronics department or computer department in your institute can offer minor with floating of 3 or 4 or 5 subjects in VLSI domain. We have just completed this one today, right? And the
Yes,
other
sir.
programs are in, yeah.
Yes, sir. The first one we have completed today. Yes, sir.
Yeah, so we have other programs in pipeline down the line. Foundation of VLSI design verification is in June next month. Testing testability is in the last week of June, and you will get information about other programs soon. So we all invite you to actually join those different programs so that you can generate your professional competence in VLSI design for the future to come. I just want to highlight the letter from Chairman AICTE, and I have these links with me. So if you want to have a look at those, I can paste them into the uh, chat box if you want that way.
So anyone who is going to speak something, please raise your hand or tell us in the chat box. Maybe one by one, Dr. Geeta can help to make the speaker
Yeah,
Yes,
on.
I'll make them as presenter, then they can
yeah.
share.
So
If they
yeah,
see us,
Please,
I will not take
those
much time,
hmm.
yes, sir.
and then leave this platform for other participant to say something. So model curriculum for minors also is there. If you want to look at that, I can share that also. And I just want to highlight what Professor Sitaraman, Honorable Chairman of AICT, has said, that they have proposed minors in many fields, and institute can offer them if their faculty is competent enough in those emerging areas. And the condition is those faculty who have gone through at least 10 credits of online courses can teach those courses. So 10 credits mean 3 or 4 courses through MOOCs, SWAM, NPTEL, or any other Government of India portal, which AICT Academy is actually. AICT Academy is actually funded by Ministry of Electronics, and whatever courses you do with us, they are counted. So this is the letter from Professor Sitaraman Sahab, and we can take advantage of that and be proficient in those part of it, right? So I take off from here and give this platform to you for your feedback. Right. Thank you very much.
Thank you so much, sir. So yes, anybody who is interested to say something, we can open it for you. We can make you presenter, and then you can unmute yourself and you can. Yuvraj, you want to say something? Debasis, would you like to say something? VLSI 0.1 has two parts. Dr. Geeta, make him presenter. Yuvraj Singh, he is having some confusion. Even I am not sure what is the question. Can you unmute?
Okay, ma'am, just give.
Yes, yes.
I think he may be referring to this slide. If required, this slide is there.
Okay.
Yes, ma'am, he can share. Yes, present.
Yuvraj, you can speak, unmute and speak. Hello.
I think he has to join back. Can he? If he joins back, maybe he can. He's trying.
He's Yeah, he's here. Yuvraj, you can unmute and speak. Can you speak? Course code VLSI 01. I can't understand what is you're going to tell about it. You can speak. I think we have given you the control for unmuting at your end. And yes, please. What is the issue?
Ma'am, on EICT website, it was showing that this course has two parts.
Yes, basically there is semiconductor, these devices, circuits and system. This is the first part, and other part we are taking into June. We are going to take. So this course is completed today, and that is a separate advanced version of this. So those who are interested, they can register. So I'll be sharing the link shortly regarding to that. Okay.
So, ma'am, these two have the value of same credit, or these two will add up different credit value?
No, no, no. Different credit. This is 3 credit separate, and that is 3 credit separate. That is the advanced. This is the basic. This is the prerequisite for that particular program, semiconductor devices and uh, sensor circuits. That is, this is the first stage. That is the second program, part 2, that we will be taking in June second week. So that is the advanced version of this. Whatever devices, advanced devices we have discussed, like tunnel FET, gallium, gate all around, pin FAT, spintronics related. So those things will be covered in that. So that is specifically for the research purpose only. And this program is prerequisite for that. So these two programs is completely separate. If you want to attend, you can register for that course separately. That is available in our portal. I will be sharing the brochure shortly. And this program is completed. It is for all. This was the general.
Okay, ma'am.
Taking to the advanced level. Whatever advanced level we have completed in this, that will be completed in the detail. That will be completed in the detail in that program. And it is going to help for the projects, for the research and other purpose. It is going to help. So I'm very thankful to Yuvraj. I found you very active in this during this FDP. You have been participated very actively in all these sessions. So I'm very thankful to you. And I hope your exams are also going on, right?
No, ma'am. Ma'am, I'm from State Government College, AKT. In this, ma'am, our session is running, ma'am, 1 month late. So, ma'am, our exam is from June, ma'am.
Okay, okay. So thank you so much. Do you have any other query? I hope your query is getting actually answered.
Yes, ma'am.
Okay, thank you. Any other participant would like to say something? So I found Ankita Porwal also continuously present in most of the other classes. Can you make her active? Ankita, she's here. Jyoti. Jyoti Yadav was also very active. Can you make her open? Maybe presenter list. Dr. Geeta.
Yes, ma'am, I'm doing. Yes, yes. They are already there.
Okay, okay. So you can speak Ankita Gupta and Jyoti Yadav. And there is one ID Dean Academics. That madam was also very active. I shared about the attendance. She is here or not? Madam, with what name you have come over here, please type in the chat box because today your ID is different. Dean Academics was the ID continuously we were having. So yes, Ankita Gupta and Jyoti Yadav, you want to speak out something related to the course? Any testimonial? You can unmute and you can speak. I think they are not interested. Okay. Sir, can we conclude it? Hello? Sir, are you there?
Bolo. I'm here.
Yes. Sir, participants are not saying anything. So can we conclude this session? Yes.
Sure. I just want to convey that Ministry has funded this program, Ministry of Electronics and IT, Government of India. A lot of thanks to them, and many thanks to our director, sir, Professor MP Padi Sahab, for his guidance and motivation. We have been doing these programs continuously for the last 7 years. This second phase, and we have a lot more things to offer. Please visit our site to see the complete calendar for the next year, this year. Thank you very much. Yeah, thanks, Menka, again.
Thank you so much, sir, for giving us opportunity. Thank you, sir. Thank you, Ministry of Electronics, MIT, and our director, sir, Dr. Nanda, sir, for the support and help, and Dr. Geeta, other staff, Deepesh, Ramesh, and Manishji for their continuous help. Thank you so much, sir, for your guidance and your support. Thank you, sir. All the participants, thank you so much for your active participation, and I hope your knowledge has been a little bit upgraded with this FDP, and let's be connected in future also with similar kind of FDPs related to VLSI. Thank you so much. Have a nice day. Thank you.
Goodbye. Have a nice day.